Welcome to the fourth episode of our drone technology series. Today, we'll discuss frequencies and communication. Technology, specifically how drones and controllers communicate. Drones are wirelessly controlled aircraft. However, this wireless link does more than just move the drone forward or upward. Modern drones do not merely process steering commands. They operate advanced communication systems that simultaneously transmit complex data from real-time video feeds to current coordinates and flight telemetry. Today, we'll examine how communication works between a drone and its controller, and how frequency technology ensures stable flight in the sky. First, let's look at the basic structure of drone communication. Drones and controllers transmit signals using two primary frequency bands, 2.4 GHz and 5.8 GHz. The controller sends control signals to the drone such as movement, rotation, or return to home commands. In reverse, the drone continuously transmits real-time video, positioning data, and battery status back to the controller. Because this two-way communication requires near zero latency, drone manufacturers develop proprietary communication protocols. Next, let's look at the characteristics of each frequency band. The 2.4 GHz band is the standard wireless frequency. Its primary advantage is long transmission range and superior signal penetration through obstacles like walls or trees. However, because standard Wi-Fi and Bluetooth also use this band, signal interference can occur in urban areas. The 5.8 GHz band is a higher frequency spectrum. Its main advantage is high data transmission speed, providing excellent real-time video quality. On the downside, it has a shorter transmission range and degrades more easily when blocked by obstacles. To solve these limitations, modern drones feature auto-switching frequency technology. They scan the environment in real time and automatically switch to the cleaner channel between 2.4 GHz and 5.8 GHz. By utilizing frequency hopping spread spectrum, or FHSS, drones maintain a stable communication link under various conditions. Now let's review manufacturer-specific transmission systems using market-leading DJI models as reference. The flagship standard is the DJI OcuSync 4.0 system. Featured in modern models like the DJI Avatar 2 or Mini 4 Pro, this digital transmission system provides smooth, high-definition, real-time video feeds up to 20 kilometers. It also features automatic channel switching to minimize local interference. Previous generation models used OcuSync 2.0 or 3.0 systems. Applied to series like the Mavic 2 or Mavic 3, these systems offer reliable connections over 10 kilometers. Older legacy models used high-definition transmission systems like Lightbridge. While revolutionary for early digital transmission, Lightbridge has higher latency compared to modern OcuSync. Finally, entry-level or toy-grade drones rely on standard Wi-Fi transmission. Connecting the drone directly to a smartphone via Wi-Fi makes the signal susceptible to interference, resulting in video lag or signal drops. With a limited range of a few dozen meters, Wi-Fi transmission is restricted to basic recreational use. What happens when severe signal interference occurs during flight? The control signal may disconnect entirely. In this situation, the drone initiates its preset failsafe mode, return to home, or RTH, climbing to a safe altitude and returning automatically to its original takeoff point. Additionally, the real-time video feed may freeze or stutter, which is hazardous when flying via screen view alone. Interference can also trigger positioning errors or temporary orientation loss. Radio frequency interference occurs frequently in dense urban centers, with high-rises, indoor venues with crowded Wi-Fi routers, or near airports, broadcast towers, and military facilities. Under international aviation guidelines and local flight safety regulations, operating drones in restricted airspace or near critical infrastructure without authorization is strictly prohibited. Here are essential signal management rules for safe operations. First, check the signal strength indicator on your controller. Screen before takeoff. Next, maintain a clear line of sight, ensuring no obstacles like buildings, trees, or vehicles block the path between you and the drone. Also, keep your controller antennas unfolded vertically, pointing their flat sides toward the drone for optimal signal transmission. In addition, if a signal interference warning appears on screen, do not panic. Climb to a higher altitude to clear obstacles or land safely. Finally, remember that the 2.4 GHz band provides better signal stability over long distances than 5.8 GHz due to its physical wave properties. To summarize today's lesson, a drone's instant response to your controls is powered by high-speed frequency exchanges and real-time data flow in the air. Understanding this invisible signal link and following safety protocols is the surest way to enjoy confident, reliable flights. In the next episode, we will cover drone cameras, gimbals, and video transmission technology. If you found this video helpful, please like, subscribe, and turn on notifications. See you on the next flight. Thank you.